First up, we have Naifeng Zhang, who will be talking about high performance portability and productivity system based on lightweight augmented neural networks. So Naifeng, if you want to start sharing your screen. And Naifeng, I believe, is an undergraduate at University of Southern California, working with Professor Viktor, Prasanna, among others. And he's going to be speaking on behalf.
All right, can you see my screen?
Yes, I can see your screen.
Okay, thank you. So thank you for the introduction, and hello everyone. I am Naifeng Zhang, and today I will present our work named towards high performance portability and productivity, lightweight augmented neural networks for performance prediction. So with various heterogeneous technologies emerging today, there have been unprecedented opportunities for accelerating applications. However, challenges remain for harnessing the computing power. For example, it is hard for a domain specialist with no expertise in parallel programming to efficiently write high-performance code. A more desirable scenario is that the user simply specifies the workload in terms of high-level operations, and the compiler identifies the best implementation. And this fully utilizes the heterogeneous platform, that is to achieve high performance, portability, and productivity simultaneously. So here is an overview of the desired system. The user only needs to write a high-level code, and the compiler will take over. As we know, most scientific workflows can be covered by few kernels, for example, matrix-matrix multiplication. If the compiler can predict execution time of each kernel, it can make better execution plan by answering two questions: which is the best variant for the given kernel, and where to execute the variant on a platform that has multiple CPUs and GPUs. Here, the variant for kernel could be different implementations or optimization flags. Furthermore, we need a black box approach for performance prediction to ensure portability, because the approach should be extensible when a new variant is available and should not be tied to hardware-specific details. Also, the performance prediction model must be lightweight, since many models need to be trained, and those models will be used at compile time as well as runtime. It needs to support fast inference. Therefore, to achieve high productivity, portability, and performance at the same time, the key is to find the lightweight black box performance prediction approach. Therefore, we propose lightweight augmented neural networks. Use the kernel matrix-matrix multiplication as an example. The neural networks takes in kernel-related parameters, such as the size and the density of each matrix. It also takes in hardware execution-related parameters, such as the number of threads that are being used in multithreading. Then we augment a mathematical function, that is the estimate of the kernel complexity, to the neural network, and this augmentation has been proved to increase the accuracy significantly. To maintain lightweight, the parameter of neural network model is kept under 100, and the model is trained with less than 1,000 examples. Our model achieves high accuracy even with a small training set in a short amount of training time, outperforming traditional feed-forward networks for all 48 kernel variant hardware combinations. As you can see from the plots, very few points have a significant misprediction. After we obtained the promising result on the performance prediction, we tested NN+C on one of these applications, variant selection. We choose the blur filter and the FFT kernel in Halide. Halide, which is the programming language designed for writing high-performance image and array processing code. In Halide, user only needs to specify the algorithm to define a kernel and the schedule to determine the parallelism in execution. Halide itself contains numerous variants, since each schedule defines a way to run the kernel. Therefore, for a given kernel, we apply NN+C to select the schedule that gives the lowest runtime. So we use the schedule shape generated by the Halide built-in auto scheduler and vary the scheduling parameters to generate various candidate schedules. The scheduling parameters are the numbers in the red rectangles. To predict the optimal schedule, we use the trained model to predict the runtime of each candidate schedule. Among thousands of candidate schedules, the true runtime of the predicted schedule by NN+C is close to the true minimum for each input dimension. We obtain 1.7x speedup over Halide auto scheduler for input dimension of 2 to the 15th on blur kernel. To conclude, augmented neural network improves performance over traditional neural network. It has fast training and fast inference. It is also highly portable as it demonstrates the accuracy on 48 kernel variant hardware combinations. Currently, NM+ is being used for more complicated kernels and is being used in compilers. Thank you so much for listening, and I'm happy to take any questions.